speaker also such that there's perfect.
Yeah. And
Until I got away to strike. Yeah.
Yeah, excellent. Okay, folks, we're going to start off here in about a minute or two. So Mick and Brian, no talking. Stand by for lunch. Ground control, Major Tom. All right. I think we're good to go, Chris. Lights, camera, action. Another minute? Okay. All right. I see everybody's gotten their seats. Welcome, everybody, to the June meeting of the Ottawa RASC. And a special welcome to other RASC Center members who may be tuning in on Zoom. We're fortunate. We were beset with a bit of a glitch on YouTube up until just very recently, but that seems to have been resolved. So for those folks online, welcome. There we go. Just to let you know that we are recording the webinar for posterity, and it will be available on our website at ottawa.rasc.ca. Also, just a quick sidebar mention concerning a bogus RASC site that has a very similar handle. It's, I believe it's ottawa-rasc.ca. Don't go there. It's a bogus site that we're trying to deal with. So just be careful when you enter the URL. Okay, regarding Zoom, we will have the Q&A available to ask questions of the speaker. And just a reminder that chat box comments can be seen by everyone. The raise your hand function is disabled. All right, and the Ottawa RASC Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and skies. I'd like to start out our meeting tonight by echoing the sentiments of the folks here at the Canadian Aviation and Space Museum on the passing of Marc Garneau, Canada's first person in space. I believe every Canadian interested in Canada's space exploration efforts were touched by sadness on the hearing of this news. Marc just passed away 2 days ago, and apparently he had a short but apparently rather difficult battle with cancer to deal with. He certainly had a storied life serving in the military, traveling to space on board the US Space Shuttle 3 times, where he spent nearly 700 hours in Earth orbit. And then after his career with that, he moved on to federal politics. There he held a number of important positions in the federal cabinet since 2015, including the transport and foreign affairs portfolios. During his time in space, he's quoted to saying, apparently he took as many opportunities as he could to look out the window of the space shuttle whenever it was passing over Canada, so he could take in our country from that rather unique perspective. So, Mark, may your spirit fly free now so that you can continue your explorations of the cosmos. Thank you. All right. So our program tonight, there you see, after I finish blabbing, Dave will do our Ottawa skies for June, and then Jim Thompson has an interesting uh, presentation on a rather unique toy that he's been playing with for the last little while. I think you'll find that interesting. We'll have our break. I'm going to do a short Astrobit segment. And then Mick Wilson, back from the wilds of Down Under, is going to talk about an upcoming adventure that you might consider, the 2028, right? Total eclipse that's happening in the land down under. So he's going to give us the pros and cons of traveling in the wilds of the outback, I think. Well, that'll be followed by observation reports and monthly observing challenges, and then just any final announcements. So without further ado, we didn't never forget to mention the new members. We still are collecting a lot of new members lately. We've got 10 on the board here and 60 new members so far in 2025. So welcome to all new members. I hope you're enjoying your stay. And for those for your first time visit to the meetings, I think you'll find it interesting, and don't feel afraid or reluctant to reach out to many of the members here who have been with us for a long time and are all too willing to share their experiences and information. So welcome again. All right, members in the news. We have John Criswick and Bernie Hasselman. John Criswick is a fellow that's down near Smiths Falls who's working on a project to basically get Eastern Ontario declared as a dark sky preserve. And they recently did an interview. Bernie was included in this with CBC, and I think do we have the video? Oh, there we go. I'm gonna play this. I think there's some commercials in it, but it's not too long.
Say goodbye to the old sorting rules. Just remember, containers, packaging, printed paper.
It may not be dark for several hours, but for many people, this area becomes a nighttime viewing hotspot. And it's a spot some people want turned into a dark sky community.
In this relatively small area, people come out to view stars. And these two men hope to draw in even bigger crowds to this area and to Eastern Ontario to view a true starlit night sky by turning the Narrows Lock, Westport, Newborough, and Chaffee's Lock area into a dark sky preserve by next year.
It's interesting to live here and be in Eastern Ontario in this region. It's pristine, it's beautiful, it's dark. It has all those attributes already.
Part of what they're trying to tackle is the growing problem of light pollution and the use of LED lights lighting up the night sky.
We're actually losing about 2% of our sky every year to light pollution. And it's not just astronomy that's affected by this, it's the wildlife, human as well.
And the rural aspect of the region makes it all the more appealing.
90% of Canadians probably live within the general population centers, and they've never seen a truly dark sky. They've never seen the Milky Way unless they've gone out camping and into a park that has a fairly dark sky.
Part of the hope is to have people limit the number of lights shining on their properties.
If you need some lights to be able to get safely down your steps or get out to your dock, great. If you want to have some lights in your garden, that's great. You can have them shielded or facing down. There are small tweaks you can do. Of course, we don't want everyone walking around in darkness. That's unrealistic.
Well, it's still likely a few years off. Their hope is to turn much of Eastern Ontario into a dark sky preserve. Kimberly Molina, CBC News, Narrows Lock, Ontario.
And we wish them luck with that project. That would be interesting to receive that designation, because we do have some very nice skies in our region. And fortunately, even for Ottawa, it's not Toronto, so you don't really have to drive all that far to get under some really, really decent skies. So we'll cross our fingers and hope they have luck with that project. All right, next up is Dave with Ottawa Skies for June. Good day. Okay. So good evening, folks. Let's see what's happening in June. Smoke. No, that's just that's something certainly we're going to have to contend with. I can't promise you clear skies. However, let's take a look at the phases of the moon. The full moon will be on June 11th. By early indigenous tribes, it was known as the strawberry moon, the time that we collect strawberries. It's also been known as the rose moon and the honey moon. And then our new moon is on June the 25th. Here's our sunrise and set times. Of course, we're coming to the longest day in terms of daylight on the 21st. Mercury is not visible. It's just tucking in too tight to the sun, rising and setting with the sun. Venus is visible before sunrise. Mars is visible in the evening. It's about the only planet right now that's really visible in the evening. Jupiter's not visible. It's hanging in tight with the sun as well. Saturn is visible before sunrise. Uranus is visible before sunrise, as is Neptune. And this is the cartoon of the month. That's being hidden by the, says the real use of the Stonehenge. That's a cat sitting in the sunlight. Now, before I move on, I was down in Toronto last weekend, and my wife spotted this amazing piece of clothing at a thrift store. Paul Cloninger's name came right to mind. I know he does a lot of winter observing. And so these are some nice woolies, complete with constellations and everything. Sold. I'll bring this around front here. Oh, you can do a bidding war on this one. There you go. All right. Yeah. So that's for you to wear when you're doing your winter observing. Oh, well, thank you. Well, you know what? I may follow in the tradition of Mick Wilson, our previous chair, who liked to wear pajama-like gear to various meetings. I may come in this one day. What do you think? Yeah? Yeah? It's big enough. Yeah. Yeah? Won't explode. I don't know. I don't think so. I just got it. I think it's mostly northern constellations. Yeah, it's more than northern. You know, the important, I mean, just the northern part. Thanks, Dave. I really appreciate that. Just show the button. I will, especially if I wear it here. Thanks again. Why did my name come to mind? All right, Jim Thompson is up for Seeing the Sun in a New Light. Take it away, Jim. Thank you.
I'm intimidated by this new podium. It's very expensive. All right, well, welcome to my talk this evening titled Seeing the Sun in a New Light. Tonight I'm going to share with you my experiences over the last few months exploring the field of spectroheliography. But before we begin, I want to warn you that I am cranking the geek level to 11 in this talk, so buckle up. Humans have been studying the nature of light for a long time. It didn't take very long for us to figure out how to use a prism to split light up into a spectrum so that we might learn even more about it. Sir Isaac Newton is traditionally considered to be the founder of spectroscopy as a field of study. He did a lot of rigorous experimentation with prisms and various sources of light in the late 17th century. Eventually, he published all his findings in a famous book called Optics in 1704. He was not alone, as a lot of other prominent scientists from the time also experimented with prisms, investigating different sources of light, just like Sir Isaac Newton did. And by the early 1800s, the availability of good quality optics meant that everybody was looking into it. Everybody was doing spectroscopy. It was practically a fad in the scientific community. The problem being it was still really somewhat of a novelty. That was until German physicist Joseph von Fraunhofer came along and did a bunch of experiments using the slits to diffract light. He played with a number of slits and experimented to see what the difference was on how light was diffracted, and he found that a diffraction grating was an efficient way of creating a spectrum. And so his design of the spectrometer involving a diffraction grating instead of a prism became a device that scientists could use to make real, precise, repeatable measurements, and therefore use it as a scientific instrument. Using his newly designed instrument, Fraunhofer was the first to systematically observe the sun's spectrum, and he found there to be hundreds and hundreds of dark bands that are now called Fraunhofer lines. And we will see examples of them a little later. But before I get too much further into the weeds, it's probably a good idea for me to explain the difference between a spectroscope and a spectrograph. A spectroscope requires a person to visually observe the spectrum through a small telescope that's on the output end of the spectroscope. And if they want to take a measurement, they have to record it all by hand. This is an example of that type of a hand recording. It was made by Fraunhofer in his observing of the sun's spectrum. You can see he was a pretty fastidious taker of notes. So this is in contrast to a spectrograph, which replaces the human with a camera or some other type of imaging device, such as what was used to take this more modern image of the sun's spectrum. This brings us to the spectroheliograph. The device was coincidentally invented simultaneously by two different scientists, George Ellery Hale and Henri Alexandre Deslandres, in the 1890s. The device is used to record an image of the sun in a monochromatic wavelength of light of the observer's choosing. These devices are still in use today by scientists, but more importantly, they are now available to amateurs. The image on the right is Hale's spectroheliograph. At the top is where the slit allows light to enter from the telescope, which is out of frame in the upper right. The light travels from the slit down to the diffraction grating, which is sort of at the corner there, and it can be rotated to change what part of the spectrum is being projected onto the exit slot of the device. You can see there's a little mini telescope here where the person can look and set what wavelength they want to look at. And then finally, the light reflects from the diffraction grating back up to the exit slot where you would place the camera, or for this particular time period, it would have been a glass photoplate. You can see that there are numerous linkages and dials, making it all look very fancy and complicated, but that was required at the time to be able to correctly align everything, focus everything, and then pan the photoplate as the telescope panned across the sun. It was all actually quite complex to generate an image with this type of a device. Pretty impressive considering how long ago they figured this out. So tonight, I'm going to share with you some of my experiences with a commercially available spectroheliograph made by ML Astro called the SHG 700. I purchased it back last November. Amateur spectroheliographs really got going a number of years ago as a result of the work done by French amateur astronomer Christian Bouille and his design of the Sol X, which uses 3D printed plastic parts for all of the body and the knobs and things, And then you combine that with an optics kit that you can buy as a package from a number of online retailers. This design was greatly improved by Dr. Min Trong, including the use of a machined aluminum housing, precision optics, and a fine focus and wavelength focus control. You can see the micrometers there on the face here for the fine control. So let's have a closer look at the inside of the SHG 700 to see how it works. Starting at the right-hand side of the image, light enters from the telescope and passes through a 7mm tall by 7 micron wide slit. Thus, the device is taking a very narrow slice of the sun to observe at a time. This slice of light is passed through a series of lenses that collimate the light and focus it onto the diffraction grating. The grating then spreads the light out so we can see the spectrum, much the same as a prism, as I mentioned earlier. This grating can be rotated by the user to select which section of the spectrum they want to project onto the camera sensor. The spectrum is spread too wide to see the whole spectrum at once. You have to look at just a piece of it at a time. Once the light reflects off of the diffraction grating, it passes through another set of lenses that focus that pattern onto the camera, which goes out here. And as I mentioned, fine focusing of the two sets of lenses, as well as the rotation of the diffraction grating, are all controlled with the fine micrometer controls that are on the other side of the device in this picture. Now this graphic will illustrate how the spectroheliograph collects data. When you place the slit, shown here as the red box, over top of the sun, you get an image of the sun's spectrum on the camera sensor, like the one shown here. In the image, the wavelength runs left-right, and the vertical dimension on the sun runs up-down, so along the direction of the lines. One column of pixels in the camera image represents the appearance of the sun inside the slit for a particular wavelength. So, for example, a row of pixels along here would be what the sun looks like along this line at that particular wavelength. And then, say, another row of pixels over here would be the appearance of that same slit, but at a different wavelength. So these are all different wavelengths along here. To collect data for the whole disk of the sun, you have to pan the telescope across and record a video to collect all that data into one file. And the result is something that looks like this, where each frame of the video corresponds to one slice of the sun as you pan the telescope across the face of the sun. So this is a single frame of the video that you would get from this process. In this case, it's an image of the part of the spectrum centered on the hydrogen alpha line, which is the most popular line to absorb the sun with. That's the thick line here that goes through the middle. There are numerous other absorption lines visible. Some of them are due to the sun's atmosphere. For example, this dark one here towards the bottom is from iron 1. But there are also a number of lesser absorption lines that are due to the Earth's atmosphere. The vertical lines that we see there, they don't change from frame to frame and are therefore due to dust or some other defect on the slit itself. But other vertical lines, like these ones over here, they change from frame to frame in the video, indicating that they are due to the granulation on the sun's surface. So as you're panning across, you're going from granule to granule, and you see that moving in the video. It's kind of neat, actually. And a little harder to see with the contrast of this screen. Oh, yes. There are some interesting things to point out before I get ahead of myself. For example, why is this line all squiggly? And the reason is because the hydrogen gas in the chromosphere is moving at different speeds. Some of it's moving towards us, some of it's moving away from us. And the result on the absorption line is that it gets Doppler shifted. That's why it has the squiggly appearance. I'll talk more about that a little later. So in addition to that, some other interesting things to note I started to say is over here, it's hard to see, and we'll see more clearly in a follow-up photo. You can actually see the chromosphere extending above the edge of the photosphere. So the edge here, the edge of the image is actually the edge of the sun's photosphere. And the chromosphere is visible above that. And we'll see better in another follow-on photo. This dark streak here is, in fact, a sunspot, as it looks smeared out across the whole range of wavelengths. And then the last thing to note is that for this particular camera orientation, increasing wavelength is down, and that's consistent for the follow-on pictures. So one of the things, being an engineer, one of the things I had to figure out right away was just how good a spectral resolution this gizmo could give me. And to do that, I started with a sample spectrum that was captured by the Observatoire de la Tourbière in France using their spectrometer that has a spectral resolving power R equal to 30,000. And if you don't know what that means, it means it's really good. This is my spectrum scaled and rotated for comparison. Using the upper spectrum, I was able to identify several known absorption lines and their wavelengths. I was also able to measure the number of pixels in my image between two known absorption lines. And doing the math, my image has a spectral resolution of roughly 0.1 angstroms per pixel. Not too shabby. And on par, I'd say, with the upper spectrum captured at a professional observatory. And in fact, if you can tell, this particular titanium absorption line is resolved as two lines in my plot, but is not resolved as two lines in the one from the observatory. So I think I might actually be getting a little bit better than they did. So that's pretty cool. So being suitably impressed by the spectral resolution, let's move on to have a closer look at that hydrogen alpha absorption line again. And here I've blown it up even more so you can really see the detail. And now you can see what I mean by the chromosphere that's visible above the photosphere. During the post-processing process, this is all done automatically by the free software. It will take all of the frames in the video that I recorded and find the polynomial that best fits through the middle of the most prominent absorption line. It just finds what's the most prominent and automatically figures out the polynomial equation that fits through the middle of that line. This single row of pixels then is used to extract the information required from each video frame needed to reconstruct the image of the sun. Each video frame being one column of pixels to go into the construction of the image. Thank goodness there's software that does this automatically and help somebody figured it out. It's pretty impressive. There are a couple of free packages out there that do this. The one that I use is called JSolX. That's the one recommended by ML Astro, and it's very easy to use, I find. Now, if you were wondering, what if I am a single stack Etalon user? How does that compare to the spectral resolution of the spectroheliograph? Well, all of the information in that bandwidth, so between those, from there to there, all that information is averaged to create your image generated using a single stack Etalon. If you had a double stack Etalon, it averages everything in that bandwidth compared to an image generated by a single row of pixels. So that kind of gives you an idea of the difference in resolution we're talking about. So I have a feeling you are all wondering, when am I going to stop flapping my gums and finally share an image generated using the spectroheliograph? Well, the wait is over. These 3 images coming up are all captured about 2.5 months ago from my urban backyard. The leftmost image was captured using a single Etalon, the middle with a double-stacked Etalon, and the rightmost using the SHG 700. The gradual increase in detail and contrast in the chromosphere as one progressively narrows their bandwidth is pretty obvious, to me at least. I find the active areas really stand out in the spectroheliograph image, as do the filaments and the prominences. The next images perhaps show this even better. These were captured 1 week earlier when the seeing conditions for my backyard were better. With the steadier seeing, you can really see the fine details the spectroheliograph is able to capture. Now, I forgot to mention that all of these comparison images are collected using the same telescope and the same camera. So any of the differences we see between Etalon and spectroheliograph is due entirely to the difference in the spectral resolution. Now, I could end my presentation on this slide. The virtues of the spectroheliograph having already been well described, but alas, there is so much more one can do with this gizmo. It behooves me to tell you all about it. Remember that image of the hydrogen alpha line I showed you earlier? Well, hidden within this single frame is a plethora of data that can easily be accessed using the software tools available. For example, if we tell the software to move, say 3 pixels down in wavelength from the on-band line, about 0.3 angstroms, we can construct an image of hydrogen gas in the chromosphere that is moving towards us at some particular speed. As another example, we can tell the software to move, say, 15 pixels or 1.5 angstroms off-band to where there are no absorption lines, and from that construct an image of the photosphere. We are free to choose any arbitrary offset from the main absorption line, offering us a mind-boggling number of ways to view the sun. The first example I mentioned, looking at Doppler shift in the chromosphere, is illustrated here. Starting with the on-band image in the upper left and then moving further and further off-band, the higher the Doppler shift, the higher the velocity. These images were all constructed from the same video data file. I only had to enter different pixel offset values into the software. Another cool output the software can produce is a Doppler gram, which gives a quick visualization of how things are moving around in the chromosphere, with blue material moving towards us and red moving away. Notice how we can see the sun's rotation from left to right in the data, as well as how the prominences and filaments are moving towards or away from us independent of the sun's rotation. You guys can see it, but this filament right here is red. That means it's moving away from us, even though it's on the side of the sun that's moving towards us. And similarly, there's some blue filaments over here, meaning they're moving towards us, even though that part of the sun is moving away from us. So that's kind of neat. You can see things are moving around. In it, yes. System.
Yeah, that good, Chris? So my question I was holding, but now with your Dopplergram, I need to ask, can you talk about exposure rates and integration time? Because I'm curious how that discrepancy between the approaching and receding limbs would be perceptible on anything other than long integration times. So is there some black magic involved?
There is surprisingly little magic involved. So if I attempt to back up here. So excited hydrogen gas. Hydrogen alpha is a very specific emission of light due to a particular electron, gets excited and drops back down to its regular orbit. So that's a well-defined wavelength. But if it's moving towards us or away from us, it gets Doppler shifted. So in this particular fuzzy absorption line, all these squiggles, it has nothing to do with time. It has entirely to do with velocity. So this is all the approaching or recession. So like over here, you mean?
The Dopplergram was color-coded red for the receding limb.
Let's go back to it here. Yes.
Okay, so it's color-coded for the red for the receding limb and blue for the approaching one.
Yes.
And so I'm given that it takes 28 days for the sun to rotate.
Right.
Angular velocities are pretty small during a single observing session.
Well, yes and no.
That's what I was wondering about.
So
Thank
because of the radius of the sun, the velocity, the linear velocity at the surface, like the difference in velocity, I don't know the number off the top of my head, but it's on the order of like 100,000 kilometers per hour or something. Like the difference from the receding and the approaching faces because of the diameter of the sun and its orbital speed. If you do the calculations on it, it's not trivial. And in fact, even if you observe the sun in the morning versus the evening, so its position is different in our sky, and our orbital Earth's velocity also contributes. So the velocities we're talking about are non-trivial. So all of this data is simultaneously recorded. So it's one video file. I just pick out different columns of pixels from the video to generate each of the images. Does that satisfy your? And the Dopplergram is literally, the background image is the on-band image, and then the blue channel is added as off-band 3 pixels one way, and then the red is 3 pixels the other way, and they just co-add them together, and that's what you get. So kind of cool, but fairly straightforward, and all done automatically. So another example of the cool things that you can get out of the spectroheliograph is shown here. This is a snippet of a video I recorded in the near UV part of the sun's spectrum, showing the two calcium-2 absorption lines, H and K. Clearly visible are bright flashes in the middle of the two absorption lines. These are active areas, plages, passing across the slit. These bright areas extend vertically as bright streaks across the whole spectrum, what we call faculae in the photosphere. We can also see that the two calcium absorption lines extend past the photosphere's limb. You have to kind of look closely as it's zipping along there. So that's showing us an edge-on view of the chromosphere limb, just like we saw in the hydrogen alpha line. And finally, you can see the occasional sunspot zipping by there. There goes there, appearing as the large black vertical streak. So let's generate an image out of this data. So when we compare the calcium K image produced using my 0.7 nanometer wide filter that I've been using for years up to this point, to that produced using the spectroheliograph, the difference is striking. Photosphere details like sunspots are gone, replaced with highly contrasted active regions and a clear definition of the megagranulation that propagates up from the convective zone into the lower chromosphere, a region some scientists call the fructosphere. What I find most impressive is that the prominences and filaments are clearly visible. Filament there, filaments here. Actually, the prominences are showing better on my screen, but this filament becomes a prominence here. So that is extremely difficult to achieve, if at all, with a conventional calcium K filter. So color me impressed.
Jim, can I,
Yes,
can I backtrack there just for a second?
sure.
We've got a couple of technical questions. Technical questions that have come in on the chat, which I believe refer to the previous slide. Chris is going to show you those. It's probably better than me reading them off.
This might be a surprise to you, Jim, but Min from ML Astro has
really?
been watching your presentation
Uh-oh.
and he's been answering people's questions.
Oh, excellent.
And you may just want to read, maybe even out loud, the string.
Okay. So, hi, I'm Min from ML Astro. Anyone have questions about the ML Astro SH3 700 can post it here, and I'll do my best to answer. Question from Oliver B. Did you move within a band such as calcium K? There is local maximum and minimum within the band, leading to high photosphere and medium chromosphere. And the answer is correct, moving to the wings of the calcium K. So by wings, we mean, back up to here. The wings means, if the middle of the band is on band, then the wings is going slightly off band. Wavelength slightly above, wavelength slightly below are called the wings. Does this show different layers of the chromosphere? Yes, it does. He's asking, did I generate different images from details in the band? That's coming up, actually. So good segue to what's coming up next. There's some very interesting mechanism that makes moving a little bit off band in calcium K actually give you more resolution. You can get low chromo supergranulation or a negative from the photosphere as the top of the convection cells are cooler than their side prior from falling through their side top of the photosphere. This is all getting rather technical. There is also a small gravitational Doppler shift from the sun, which would be mostly constant from the sides. Then there's another question from, oh, this is Olivier. Okay, I know who this is, yes. You didn't see necessarily the same layers as you move within the band, switching from the high photosphere slowly up to the low mid chromosphere. So just to bring it on the context, The temperature of the gas we're looking at determines what wavelength of light is given off, and the temperature of the chromosphere changes as you go from the bottom to the top. It increases. So by looking at gases of different temperatures, you can, in essence, look at different layers of the chromosphere. I think that's it. Oh, Min says hi. Hi, Min. Thanks, Chris.
Paul can tell you if there's any more on that message string.
Yes. Oops. Yeah, I can hear you, but nobody online can hear you. So if you...
The shrinking and expanding of that picture there, is that because the slit is running over a fat part of the sun to the edge of the narrower part?
Yeah, so I've rotated it so that it fits on the screen better. But in essence, this is starting from off the side of the sun and panning across. So it's getting larger because
It's wider sun.
It's wider, yeah.
Okay, the other thing too, the next question I asked was, going to ask was, when you do a scan of the sun, how many little rays, I mean, how many chunks do you break the sun into?
So there is tools in the software that helps you to align the scan rate with the frame rate of the camera. And the objective is to have each frame of the video correspond to the distance to one slit width, basically, while you're panning. So depending on how fast your camera is, what exposure you're running at, those frames per second needs to be, to get the best result, needs to be aligned with the pan rate of the scope, and there's a tool to figure that out. It is on the order of, for me, for my camera resolution and telescope resolution, it's about 5 to 7 times sidereal. So it's a custom rate. You have to custom control the mount, which you can do from, I use SharpCap, and you can custom control the mount with script language. Sure.
I'm afraid this might be a really elementary question. Yeah. You're referring to this as an absorption line, but when I look through my H alpha telescope, I assume I'm looking at something bright, not something that's missing.
No, in fact, what you're looking at is the absence of photosphere light. So most of the time, hydrogen alpha or calcium K, the same case, is too dark for us to see. It's being overwhelmed by, so all the other light, all the light that's in here, that's all getting to your eye when you're looking at the photosphere, and it way overwhelms all the other light. So by using this type of a device or an Etalon, you're blocking all of that light and only allowing the little tiny bit of light coming through here. And that's why we're able to see the details that we see. We're not seeing all of the rest of that bulk light coming from the photosphere. Because this is all stuff sitting between us and the photosphere. It's kind of overwhelming it.
So there's no H alpha filter between the spectroheliograph and the rest of the telescope?
No, it's sun telescope spectroheliograph. There's no energy rejection filter, and that's one of the good aspects of Min's design is you don't need to have a energy rejection filter, which gives you a much brighter image, means your exposure times are low, you can get around the seeing, and you get a nice, a better quality image. All right. I will answer questions at the end in case anybody was worried about that. Anyway, moving along. So yes, that's calcium K. And as I mentioned, I am suitably impressed by the ability to see filaments on the face of the sun in calcium K. You'd never be able to do that with an Etalon or a conventional filter. Another example of things that you can image is helium D3, which is an emission line, not an absorption line. This is an image generated from the line of pixels corresponding to the helium D3 emission, or at least where it should be in the sun spectrum. You can see there's some very subtle details there, but really not much to write home about. Well, if we now subtract from that image an image of the photosphere that I constructed by using pixels 1 angstrom away from the helium D3 line, and then doing some Photoshop hocus pocus, you get this image. So there is some very funky stuff going on there. I don't really know exactly what it means, but it's cool nonetheless, including the fact that you can see prominences in helium D3. And is actually one of the reasons why when I went to the eclipse in Mexico, that's over a year ago now, that I got a flash spectrum, because you can see chromosphere in a flash spectrum in helium D3. It shows up. You can see prominences and the chromosphere in that band. So anyway, sidebar. So the last cool imaging thing that I like to talk about is magnetograms. This is on my to-do list, to figure out how to use my spectroheliograph to generate maps of magnetic strength and direction like the ones shown here. Magnetograms were instrumental to scientists figuring out the sun's activity cycle and are still used today to monitor the strength of active regions and to track the transition from one solar cycle to the next. I believe it's possible. I just need to figure out how to do it practically. So having had some time now to work with this spectroheliograph, I am able to give my opinion on it, starting with the pros, of which there are many. As I already described, the spectroheliograph delivers an extremely narrow full-width half-maximum bandwidth, an entirely different league from what filters and etalons can deliver. Spectroheliographs generate images with uniform illumination of the whole solar disk, with no Newton's rings. You may have noticed some Newton's rings in my earlier images with the etalon, and no hotspots or bright areas in the disk, something that is challenging to do with an etalon system. You have access to a large multitude of wavelengths to image the sun in, all with one compact device. You also have the ability to get pretty good results with less expensive telescopes, like achromatic refractors, as long as you have them on a decent motorized mount. Now, I haven't tried this myself, but other users of the SHG 700 have been very successful using it to collect spectra of other kinds of objects, such as planets, stars, and even planetary nebulae. Compared to other options for observing the solar chromosphere, the spectroheliograph is relatively inexpensive. The SHG 700 I have presently selling for only $880 US. Finally, I have found the SHG 700 to be very well designed and built, and it has been a pleasure to use. In terms of cons, I have identified a couple. The first one being the workload required to get a decent image is somewhat complicated and heavy. To give you an idea what I mean, consider this list of steps required to collect image data with an etalon or filter setup, compared with this list of the steps required when using the spectroheliograph. The spectroheliograph requires numerous focusing and alignment steps, followed by a very specific data collection routine, making the process significantly more complicated than what one would be accustomed to using a more conventional etalon or filter setup. Now, some automation is possible using SharpCap's scripting language, but this only saves effort during the data collection steps. The remaining steps still require manual intervention. The second con I have found is that lucky imaging is out. Unfortunately for me, my seeing is typically poor, so lucky imaging is my saving grace. This is a zoom in on the double-stacked etalon image you saw earlier. It is a stack of the best 200 frames out of 4,000, sharpened in IMPPG. As you can imagine, the data that I collect in one solar session is huge. It's on the order of a terabyte of data. This is the comparable view taken with the spectroheliograph. It is a single scan with only histogram stitching applied. I imagine you share my reaction seeing this result. Gah! The image quality can be improved by taking multiple scans and stacking them, but it just is not practical to collect 4,000 scans, process them, and stack the best 200. A single scan alone takes almost as much time and disk space as it does to collect 4,000 frames with the etalon setup. So, to realize the full potential of the spectroheliograph, one requires good seeing conditions. That being said, even with my poor quality urban skies, I have been finding great enjoyment with my spectroheliograph. An example of which is this collection of hydrogen alpha images that I was able to capture using the SHG 700 on 4 consecutive Sundays this spring. What are the odds of that? These colorized images with enhanced prominences are one of the outputs generated automatically by the JSolX software. And if you compare the images, you can see that there is quite a bit of difference in the quality of the result, entirely due to the seeing conditions. For example, the 20th is not nearly as crisp as like the 27th or the 4th. So yes, seeing has a big impact. I managed to collect a similar sequence of images in the calcium 2K band as well. I find it fascinating how different the sun can look from one observing session to the next. I haven't been just cranking out pretty pictures, though, if you were wondering. I have also been hunting for new things to pull out of all this newfound data. Now, if we go back and look at those calcium 2 lines I showed you earlier, take note of the appearance of these absorption lines compared to the others. The H and K lines both appear big and fat. And this got me to thinking. Is there something, I often put a monocle on when I'm thinking. Is there something interesting going on if we look around inside these wide absorption bands, in the wings, as it were? So let's take a look. So this is the calcium K image from May 4th that we just saw a moment ago. It is an interesting image on its own with lots of prominences and filaments visible and a great smacking active area in the middle there. Now let's have a closer look at the prominence that's up top. Here is that area viewed at 5 different wavelengths. The band shift noted there in the red text. The prominence is nicely visible in the on-band image, but quickly disappears as we look more and more off-band. Kind of what we would expect. Now let's check out the prominence in the lower right. Again, the prominence is clearly defined in the on-band image, but you will notice that portions of it persist, even at a half an angstrom off-band. What we are seeing here is material that is moving towards or away from us at high speed, fast enough to Doppler shift the emissions wavelength. Take a closer look at how the shape of the prominence changes as we move off band. Using our imagination, we can visualize how the material is moving around. Keep in mind that these images were all captured at exactly the same instant in time. My interpretation of what we are seeing here is that the prominence material is spiraling around some invisible magnetic field line, thus presenting itself to us as moving up, down, and towards and away from us, all at the same time. The observation of Doppler shifted material is taken to the extreme if we now zoom in on the left side of the sun. The on-band image doesn't really show us much of anything. But at longer wavelengths, we can clearly see that there is something going on. The prominence material is clearly visible even at 0.7 angstroms off band. Oh, it's quite dark here. I guess you guys can't really see that, eh? There's it's very faint. There's prominence here. Yeah, it's much better on my screen here. Well, when I found this, I was quite intrigued, and I went back to my source data to see just how far off band I could see that prominence, and the answer is 0.9 angstroms off band. Now we can calculate the rough velocity of the prominence gases using the band shift number and a simple equation involving the speed of light. That's it in the lower right there. So for the material that's visible at 0.7 angstroms off band, we get a number of 53 kilometers per second as the speed of the gas moving away from us. And for the 0.9 angstrom material that I didn't show here, but I found in my data, we get 69 kilometers per second. That's almost 250,000 kilometers per hour. You can circumnavigate the Earth in about 10 minutes at that speed. By the way, I searched all of my spectroheliograph images in the H-alpha band from this day, and this fast-moving prominence was curiously not visible. To do more exploring on that one. So that's it. I hope you've enjoyed my talk. As you've probably gathered, my adventures with the spectroheliograph have been fun and mentally stimulating. Compared to other options available for chromosphere observing, the spectroheliograph is very capable and quite affordable. Although I do have to say it is not for the faint of heart. It is highly technical and it demands a heavy workload, a geek level 11. And now a final word on the ML Astro owner, Dr. Min Trong. It actually is in here. I didn't just add this knowing that he's online. It's printed, you can see, right? I have found him to be very responsive to my inquiries, and he is extremely generous with his time. I highly recommend ML Astro as a vendor. And that's it. Thank you very much. I got a waving hand at the top there. That's Chris. I did bring my SHG 700 tonight, and you can all come take a look at it during the break if you like.
Here's a question for you, Jim, from the chat line. All of this spectrum information is very interesting, but is there any practical use to which the information can be used?
If I was a scientist studying the sun, absolutely. I'm just a casually interested amateur. I find it intriguing to see the sun and all these different wavelengths, but all of this data is very useful for monitoring and predicting how the sun is going to affect the Earth. Seeing mass ejections of materials, seeing active regions that have high intensity, a lot of sunspot activity, monitoring all of these things is important for having some sort of a heads up on whether or not the Earth is going to be impacted by a solar storm, which in our progressively more high-tech world is very important. Does that answer the question?
Good answer, I think. We have one over here.
Just a quick one about the kind of telescope you can use with it. Given that the sun's energy is unfiltered coming down the tube, is it best that it not be a scope with optical elements near the other end of the scope, like a Petzval reflector?
That's a good question. A question that would probably be best answered by Min if he's listening. But I would say yes, that's not a good idea, because the slit is highly reflective, and a large percentage of the incoming light gets reflected back up the scope. So that might not be great for a Petzval that has lens elements right there ahead of the focus point.
We have another one, Jim.
Hi, Jim. That was a really interesting talk. But I had one question. Does that spectrohelios graph have a second synchronized slit? Because step 7 in your workflow suggested that you were adjusting it to filter out one particular spectral line. And yet your videos, you're collecting the entire spectrum, the entire visible light all at once. Because traditionally, spectrohelioscopes and spectroheliographs have a second synchronized slit synchronized to the first one, and you can get one image without using software, which is how they were originally built.
Yeah, you could see all the linkages required to make that happen in the image that I had up earlier. So there's a slot where the camera goes, and it moves as the telescope moves to develop an image on the photo plate. That's how they used to do it. In this particular case, there's a trade-off between spectral resolution and how much of the spectrum you can see on the sensor at once. In this case, the decision was made, and rightly so, to use a diffraction grating that results in quite a large spread rate. So I can only really see on my camera sensor, try to remember, maybe 50 nanometers worth of the solar spectrum at a time, because it's just spread at too rapid a rate. It can't all be imaged at the same time. And the purpose is to get that the angstroms per pixel to where you can now resolve all these fine details, like in the H-alpha line, the calcium K line, etc. Does that answer your question?
Yeah, just out of curiosity, I built a spectrohelioscope back in 1990 based on plans from Sky and Telescope that published them in 1970. But it didn't work, though. All I had was hand tools to work with. And obviously these things are very finicky and you need high precision components. But anyways, that was a great talk.
Yeah. Thank you.
Agreed, great talk. If the image on the camera is only 15 nanometers wide, in order to scan through the whole spectrum, do you manually rotate the diffraction grating? And each time so when you say you get a video, is that while you're manually turning the dial for the, how does the, what's the
No,
video part?
the scan, when I say scan, I mean panning across the sun. So the slit's only giving me one line of the sun's image, and I have to move that line, that slit across the face of the sun to get all of the sun's disk. Correct. But I have to decide before I do that what part of the spectrum I want to image. So I manually set where in the spectrum I want to image. Once that's all locked in and I've refocused the collimation lenses, the camera lenses, the telescope, all have to be focused each time you change the wavelength. Then you can collect the data. And if I want to then move to calcium K, I have to redo all those steps again.
Great. I think we have time for one more. I'm hoping that Jim will be available during the break.
Oh, absolutely. I'll be around.
There you go.
Oh, we got a fight over here. Settle down, guys.
I just wanted to say that reference, I think it was Michael's question about, you're looking at absorption lines. That last couple of slides where you showed the prominence, you can see that on the absorption line, it's quite a bit darker. There's still lots of emission, but once you get off the absorption line, it gets much brighter.
Yes.
Because of the lack of absorption. So it's additional detail. It's kind of neat. Thanks for the talk. It was great.
You're welcome.
All right, Simon, you did have your hand up. So,
Jim, right at the beginning, you showed us a professional spectrum.
Yes.
And you told us the R number, 30,000.
Yes.
Then you showed us yours.
Can I?
Then you showed us your spectrum.
Yes.
And you pointed out that it was at least as good.
Yes.
Did you have the wherewithal to calculate the R number?
I didn't. It's something I should discuss with Min, how it would actually be defined, because I believe it has to do with how far apart two absorption lines can be, or how far apart they need to be and be resolved as two lines, which would imply that each pixel is 1 angstrom. So I think that means that, or 0.1 angstrom, I think that's 0.2 angstroms before I can resolve two lines. So that's my limiting resolution is 0.2 angstroms. And you divide that by the wavelength of light and you get the R number. Or sorry, wavelength over the angstroms and you get the number. So I think it's in the same ballpark. That image wasn't as well focused as I'm able to get now, so I think I would be even better, but it's up there.
Super.
Right.
Well, that was amazing, Jim.
Look at that. They put my announcement slide right in there. That's good. Thanks, Chris. So while I'm here, I want to send out a huge thank you to all of the volunteers that came out on Astronomy Day on May 18th. It was a huge success, even though we were kind of like, oh, it might be better with clouds on Sunday. We said, let's go for it. And ended up the evening was, even though it was still a little cloudy, we still had great views of the moon. We had a great view of a crow's nest, a raven's nest during the day. Everybody loved it. People were gushing with appreciation. The photo here was a panoramic that I took around 9 o'clock, and there were lineups, multiple people deep for all the telescopes. So it was a great success. Thank you, everyone. See you in 2026 on April 25th. Haha. And as a side note, there was a Astronomy Day live stream running hosted by RASC National. They went from coast to coast, showing what each center was doing for Astronomy Day, and we were the only center doing sidewalk astronomy. So well done, everyone.
Right on. Thank you. Jim, I don't know if you can access this on your cell phone, but if you want, feel free to use the computer there to scroll through the chats.
Oh, the chats?
Yes, feel free.
Okay. Thanks.
All right. Well, that was pretty amazing. And when I reviewed the slides and now that I've heard Jim's presentation, I'm just amazed at well, let me put it this way. Having worked on a couple of presentations with Jim when we were doing our lunar stuff there, I was impressed at how deep down the rabbit hole this man can fit. And and compared to those presentations, what I see here now, man, you must have a built-in drill or something to get down those rabbit holes. Well done. Absolutely well done. All right, and you've got way too much time on your hand, by the way. We have one announcement. Do we have Sharon online? You can't what, sorry?
Hello.
Oh.
I'm online.
Okay, so Sharon's gonna share something on the Dominion Observatory with us. Go ahead, Sharon.
Yeah, tomorrow is Doors Open Ottawa, and the Dominion Observatory is open for tours this year. So tomorrow, the 7th of June, and we are celebrating the 2025 National Historic Site designation of the Dominion Observatory campus. So the forecast for tomorrow is supposed to be sun, maybe a few clouds. Now it looks to be really sunny, but maybe there's smoke, I don't know. But if the weather cooperates, the solar viewing can occur. Is anyone able to come by with a telescope? You're more than welcome. And I know that there's a couple of RASC who will be coming, but more is better. The 2025 Door Open theme is Green Spaces in Ottawa Historic Landscapes. And Ottawa Centre RASC members are volunteering on outdoor tours of the observatory campus buildings. And please join us if you would like to volunteer too, or drop in for a visit to lend support. Thank you.
Thank you, Sharon. Great. All right. Well, I think it's time for a bio break. Feel free to come down and have a look at the swap tables, but I do ask you to keep it to 15 minutes because we do have a bunch of things still to go through tonight. And go stretch your legs. Talk to you in 15.
Two speakers, Vicar Abbasi from CSA on NeoSat.
Oh, nice.
And the other guy is Min Tran from James Webb was talking about
I've heard the name, yeah.
going through all the anomalies and stuff and how they're scheduled to get maximum observations on James Webb. So
Right. Awesome.
I'm supposed to get his contact details. He has mine, but
Okay.
like after the conference finished the end of last week, but they're taking so long just compiling all the gazillions of papers that
I'm
we
sure.
save in space ops to get that done. They should get the whole line.
Okay, I'd really appreciate, actually, could you send me the details once you get them?
Yeah.
And
Send it
I'll
here
fol-
right away.
I'll follow up on that.
I told them I'll,
Yeah.
I'll let them know, and I told them.
Yeah,
Fine to do remote, so. that
Yeah.
Presentations remotely, I said,
Yeah.
we got high production values at Rask, Ottawa, so.
Excellent.
They're very keen in doing this.
I've got speakers scheduled into the fall already.
I told them like it'd be 2-3 months. At
Oh, yeah,
earliest.
yeah, at the earliest, yeah. I've got full slate booked. I've got one half spot, I think left in November. And then I'm also looking for speakers for the dinner.
Oh.
So it's one thing I wanted to talk to you about, Chris, because I've got a handle on
Maybe one of these guys
Yeah.
that might be intrigued by coming to Ottawa for the
Yeah.
dinner, so.
Yeah.
Yeah.
But yeah, please do send me those details. I'll I'll definitely follow
I'll
up.
let you work that out with them.
Oh, absolutely, yeah.
You feel you can
And can I,
slot them in.
yeah, and I'll tell them that you sent me.
Yeah, they know.
They
Yeah,
know you?
Yeah, I've talked.
Okay, folks, I'm going to give you the 2-minute warning here. What did you buy, Rick? All right. Pick her up. Hope you enjoyed your bio break and your chat break. Just a quick go through. I'm going to speed some of this up because we've got a fair bit of stuff still to go through, and I wouldn't want to be late. No comments, Simon. Anyway, benefits of joining our club if you're just visiting and taking it in. I hope you've enjoyed the session so far. Benefits of joining are numerous, including all the people that you see here and more. We have a few hundred in our club actually, and being part of the club gives you a chance to meet and engage with many of those people who are more than willing to share their knowledge and experience with you. Also, we have a loan library of books as well as telescopes, the Ted Bean Loan Library, and these are available to our ASC members where you can borrow a telescope before you contemplate laying down a lot of money and buying one. It's the old try before you buy thing, and sometimes you can get you can avoid yourself some grief. Anyway, that's available for members. We have Estelle's library. She's with us tonight, and so if you want to browse the library, she'll be more than willing to show you what we have back there. We also have a number of goodies that come with your membership. You get a monthly summary of things in our Astronotes done by Gordon Webster. The journal comes out, which is a sort of a higher end publication written by typically members of the society on various different technical subjects. And we have the Venerable Observer's Handbook, which has been around for many, many years and is still a staple for many because of the wealth of data that it contains. Especially useful if you're out in the wilds poking around with your telescope with no internet connection and you really need some data. That's your reference point. All right. You also get as a member, you're entitled to an Astrospheric Pro level subscription. Outside the club, this costs you $66 a year, but it is a benefit with the club. This is a pretty amazing program with a lot of environmental data to help you plan your observing sessions. You can also have access to the Discord server, which is a chat group for basically members only. And yes, speed things along. As membership fees go, regular membership is 113 per annum. Family membership is 107.50 for the first adult, and then $15 and $9 for family members. And we also offer the youth membership at $72.40 per annum. All right. Okay, I'm going to rush through this. This is an Astrobit segment that I put together just to give you a bit of an update on something that I talked about a couple of months ago. You may recall I did an Astrobit segment on a paper that I'd read about the potential that the Earth had a ring system around it about 500 million years ago due to the capture of an asteroid that passed nearby, and the Earth's gravity was able to snare that into an orbit. Basically, that asteroid orbited the Earth for some time, fairly large asteroid, but eventually encroached within the Roche limit of the Earth, and basically was shredded by the gravity of Earth. What happened then subsequently was that once it was shredded, the larger segments started to come down. They started to deorbit and create numerous large craters on the Earth. This is all from that paper, from the study. They did a really interesting analysis, and what they found was that a number of the craters in North America statistically were in a position, if you look back at the paleo geography at the time, that they looked like they struck boom, 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 like in a line, essentially. And of those craters, the Brent crater up in northern portion of Algonquin Park is considered possibly one of those impact sites created by this deorbiting material. It's a fascinating paper and well worth the read. Anyway, our resident crater expert, Chuck O'Dale, and I, after I gave this presentation, we started chatting about this, and we thought, maybe it would be a good opportunity for an expedition down into the crater. And so we organized that, figured out what we were going to do for a couple of different reasons as well. And you may recall some of this from the invite that I extended to everybody to join us on that hike back. I sent that out in the middle of April. Anyway, on May the 8th, here we go. We actually journeyed up to the Brent crater. There were 6 of us in total that went up there. This is a view from the observation tower that exists on the eastern rim of the crater. It's a nice observation tower. It's fairly high, and it gives you a look over the treetops. And you can see on the horizon, that is the far western rim. This crater is about 3 kilometers in diameter, so it's not just a little pothole in the Canadian Shield. It's a fair size, and there is a recognized trail that goes down into the crater. It's a loop trail about 2 kilometers in length, if you're ever interested in going up there yourselves and seeing this. But Chuck and I had a slightly different thing on our minds here. You can see, if you look closely, and see if I can get it with the laser, right up there, that little blue patch. There are 2 lakes in the central portion of the crater, lakes that have, I should backtrack. The crater's been filled over time. Remember, this was from about 450 million years ago. The crater has been filled in over time with a lot of sediments from glacial movements, and but there are still features available. Currently, there are 2 small lakes in the center of it, and or surrounding the center of it. And what we wanted to do was venture to a site that Chuck actually found. I'll backtrack on that. That Chuck actually found not far from that one lake. I'll give you more on that here in a second. So we wanted to explore this. I was up at the site actually last year, and I just did the standard 2 kilometer trek and collected some samples from one site there. But Chuck made an interesting discovery about 20 years ago. For those of you that aren't familiar with Chuck, he is our resident crater expert there. He has visited most of the impact sites in North America. He actually flies there. He's a pilot, and he has his little Cessna there, and so he's done some extensive exploration of these things. And 20 years ago, he was down in the Brent crater and discovered a feature that doesn't appear in any of the guides in that. And so I was very interested in hearing about that, given my interest in geology as well as astronomy. So what we did is we organized the trip. We had 6 folks ready to do a bit of a hard hike, and down we went into the crater. So first site that we went, this is on the trail, and this is one of the few sites in the crater where there is some exposed rock. Most of this, like I say, most of the crater is filled with sediments from glacial movements over the ages. But this particular site is believed to be a piece of debris from the rim itself. It's talus, basically, stuff that has crumbled down from the rim over time and is exposed in this location. It's fascinating. I collected some samples from this last year and had a look at it, and I thought, I've got to go back to this site for some of the stuff that I found in those samples. So this is just a few shots of us. I'm not going to go into a lot of detail here because Chuck is going to give us a detailed look on his explorations, including this one in November. He's going to give us a major talk on that. But needless to say, we were looking for certain features in this rock because it's one of the few things that may exist from the original impact that isn't buried under hundreds of meters of glacial sediment. So you can see from the picture itself that the rock has a very fractured appearance to it, and certainly, even though the rock itself, like it's Precambrian crystalline rock, it's hard when you hammer into it, but it has numerous fractures, and that's where you can calve off chunks fairly easy. These fractures are believed to have been caused by the blast itself, which is calculated to have been about the equivalent of a nuclear device of 250 megatons. So 4 times more powerful than anything we've detonated on Earth. So interesting samples there. And I'll just speed through that. There's Chuck and Andrew Brown, who joined us on the expedition, looking at some of the samples that they recovered as well. Pretty fascinating stuff there. There's yours truly geeking out on one of on that rock outcrop collecting samples. I was looking for very specific stuff, which I'll tell you about in a moment. And then we went off trail. So as I mentioned, the loop trail is about 2 kilometers. Chuck's Canyon, weren't exactly sure where it was. So it was a bit of an exploration thing, a bit of trial and error. We had a rough idea. But when he discovered this site 20 years ago, he named it the Mini Grand Canyon, because there's no other feature like this that, at least that we know of, in the basin of the impact crater. As I say, in this one, nobody seems to have documented this. So we were determined to find this, and after doing about 2 kilometers on the trail, or 1.5 kilometers on the trail, we then had to bushwhack through the forest, basically no trail at all, for about, I think Chris calculated the length. Our hike was about 6.3 kilometers. So there was about 4 kilometers of sometimes pretty intense bushwhacking to get to the site, but we did find it. You can see Andrew taking pictures. There's Chris and Louisa in the foreground, and Andrew taking pictures. It's an impressive site. It is a canyon cut through a similar rock cut to the one that I mentioned, but it's much higher, much more extensive. And there's a stream flowing through it. You can actually see there that is believed to have cut through most of that over many, many, many years. All right. So as you can see, this is from Chuck's Mini Grand Canyon site. There's a lot of fractures in this rock. Like there's clearly been a bit of stress going on here. But again, I will let Chuck talk to this in more detail. I just wanted to show you this. Gives you an idea of the height and the size of this particular feature. We spent a fair bit of time there poking and prodding the geology and taking pictures, just because it was difficult to find, but it was certainly well worth the hike. So everybody was happy. We didn't have any injuries. Nobody fell off a cliff or drowned in the lake or anything. It was a very good experience. So just a couple of samples. When I got home, I cleaned up. I brought back about 3 pounds worth of samples from 3 different sites, actually. Most of them from the mini Grand Canyon and from the original outcrop sites. And there's some really interesting geology happening in this. I'm not going to go into detail because Simon's there, and yeah. I've got to be cautious. I know you didn't. You're a good man like that. But you can see some interesting geology, and some of the samples I collected. You can see these much more ancient features, and you can see lines, hairline thin fracture lines running perpendicular to the flow of the material here that caused features like this. And when I look at it, I also looked at these features with a small microscope, and this is what I was after. I recovered a few samples from my trip into Brent last year, and one of them showed me some interesting stuff here. And at the risk again of stepping way outside my pay grade, it's the black stuff that I was interested in, because when I first saw this, it took me back about many years. One of my jobs after finishing university and before coming to Ottawa was that I worked in the Falconbridge nickel mines, actually in the smelter. And I saw a lot of examples of molten slag hitting rock and stuff like this. And when I saw this in the microscope, I thought, Jesus, that looks an awful lot like that, but on a much smaller scale. And interestingly, the samples I collected, I was doing this kind of very systematically. I was taking samples because I wanted to see the inside of the rock, and I wanted to see the outside facing portions. And it's interesting that a lot of these slag-like features, if I can call them that, were only on the outer facing portions of the samples that I collected. I know there's probably a new basket load full of geological processes that could account for this, and really I guess the only way to determine what that stuff is through analysis. But it made me think, is this stuff that got splatted out from the original impact and just got pasted on some of the rock? I don't really know. We should have a talk afterwards, Simon. There we go with that. And here's a sample from the site that's on the official trail. Again, believed to be a slide of talus from the original rim. And again, with the microscope, looking at some of these features, they certainly, to a non-geologist like me, appear as though they're almost melted on there. So pretty fascinating stuff. And I will leave it at that. If you have any questions, feel free to approach me afterwards. And without further ado, yes, I'm going to turn it over to Mick, the man, who's going to talk about places down under. There you go, sir.
G'day. So here's your fair income true blue bonza cobble wallaby guide by a friendly native to the July 22nd, 2028 eclipse of the sun. And that's going to be in Australia. Where's the gizmo? For those of you who aren't familiar with Australia, that's how you find it. You go to Vancouver and just keep going, and 15 hours later, you're in Sydney. Very straightforward. The proper orientation shown on the bottom left there, but I will Boreo-centralize it for you people. And so there we get the map. All eclipse presentations must have the map. And as you can see, moving from the west over Indonesia, it's coming down through, well, I might as well use the gizmo, yes. So Indonesia, coming down into northwest Australia, a region called the Kimberley, very much across central Australia, Ayers Rock, for example, is down here somewhere. Cutting into southwest Queensland, the area that had all the floods a month or two back, and then down across and hitting the east coast right at Sydney. Like you could fly into the airport, look at the eclipse, and then fly out again 20 minutes later, whatever. Any questions? Okay. There should be questions, because otherwise this is just too good to be true, right? Which one? This one or the other one? No, it's fine. Fine. Okay, so there's Sydney. Okay, right on the coast, it's very close to the centre line. And from Vancouver, as I say, 15-hour flight. And I mean, the price is not unreasonable. It's $2,500 a person in normal economy. You can get cheaper. You can obviously pay more. It's survivable. Everyone says, oh, it's so far away. And it is, but it is survivable. So along that eclipse path, you have Sydney, and it's going to get 3 minutes, 49 seconds of totality. And that's about the same as we got in Quebec in April of last year. Further west you go, longer the duration. Best is there at the point labeled Devil's, whoops, that was my mistake. Devil's Marbles there, right in smack bang in Central Australia, where you're getting 5 minutes and 10 seconds of totality. That's pretty bloody good. Now, two bad things about Sydney. One is it's not my hometown, Warragul. And if you go to Sydney, you won't go to Warragul. And that's just not on. And secondly, the eclipse path is nowhere near Rottnest Island, which means that this presentation has no quokkas in it except for that one. That's it. So back to Sydney, 3 minutes, 49 minutes totality, 3 minutes, 49 seconds totality. Local pronunciation, nobody says Toronto. Nobody goes to Toronto. In the same way, nobody goes to Sydney. It's Sydney. So what do we know about Sydney? Opera House, Bridge, Harbour, that's it. You've got all the major tourist attractions there. It's Australia's largest city, 5.3 million. So again, it's not quite Toronto, but it's getting up there. World famous harbour. It's got great beaches, except you're going to be there in July. Whoops. Many famous attractions, the Opera House and so on and so on, and a smack on the path of totality. I'm here to convince you why not be in Sydney. Why go beyond Sydney? Yes, it's easy to get to. It's civilized. You can drink the water, all sorts of things. People speak English. Why not Sydney? A number of reasons. One is it'll be July. That's our winter. The weather in Sydney is likely to be very dodgy, or possibly even, as we say in Oz, absolute crap. This is not a good place to be for eclipse spotting. It is crowded, and it will be more crowded because of the eclipse. It is an expensive place. Accommodation, eating out and so on is expensive. It is a city. There's no Oz experience. It's a damn shame to spend 15 hours flying across the Pacific to end up somewhere which, yeah, okay, it could be Vancouver sort of thing. It's just not proper Oz. And you will not have any dark skies at all. It's a complete urbanation, and so forget that. So back to the map and the reminder. Just like Canada, Australia is mostly empty. 95% of the population are in Perth, Adelaide, Melbourne, Sydney, Brisbane. All the rest of that green area is rural population, small centres. You wouldn't even call them towns. You know, there's places with population to 4,000 or 5,000 people. That's a town. Here you call that, I don't know, crossroads or something. So Australia is a vast empty land, much like Canada, but with better beaches. The reason nobody lives there is because it's too damn dry. And from an astronomer's point of view, that's great. As soon as you get away from the coast across the mountains behind Sydney, the Great Dividing Range, prospects look up, literally. Whoop, don't know why I went back to Warragul. Now, here's part of your constraints in thinking about this. Apart from getting to Oz, getting around is has its challenges. And as we know, prime requirement for eclipse chasing is mobility. As you know, many of you found or relearned back in last April, where predictions were off at particular sites and it was too late to move elsewhere. Travel networks in Australia are thin, they're long, and so your options for packing up and moving to get out from under the clouds are somewhat more constrained than here. And remember, you won't have anything like astropspheric working in Australia. I haven't found an Australian version of it. So those are the major highways in the country. What does that mean? Well, Melbourne to Sydney is 900 kilometres. So that's like here to Toronto and back. It's a 10-hour non-stop drive. Of course, everyone has to stop. So it's a long day, Melbourne to Sydney. And it's Australia's best intercity highway. And that's what it looks like. It's 4 lanes. It's, it's like the 417 here. It's not a super expressway. It is just a 4-lane highway with graded ramps and so on, limited access. 900 kilometres of that. To get to the next city up the coast there, Brisbane, that's 1,000 kilometres, which is here to Toronto and back and to Toronto again sort of thing. That's a 15-hour non-stop drive on the next best intercity highway, and it looks like that. Okay, it's like Highway 5. It's 2-lane, it's well graded, well maintained, and so on, but it is a 2-lane road, and you get stuck behind a truck on something like that, and it becomes a long day. Most of the roads, to get out to places like Burke, which is on our eclipse path, and I'll come back to in a minute, that's 800 kilometres, a good 12-hour drive on a normal rural highway, which looks like that, up to and including the wildlife. Kangas, emus, whatever. All I'm saying is if you're thinking of going to Oz in order to witness this eclipse, you're going to have to plan your logistics. There's lots of good reasons to go to Oz apart from the eclipse. I mean, the spectacular landscapes, as I said, the beaches, and so on and so on and so on. And so getting around for the eclipse also gets you to some of these top spots. Why am I pushing for you to head out into the outback? There will be far, far better prospects of clear blue skies. Like I say, as soon as you get away from the coast, as soon as you get over the mountains, well, it's a bit like California, I guess. You get over the Sierra Nevada or whatever, and you are in dry country. You will see proper, real dark skies. I'm talking world-class night observing opportunities. I'm talking about having your shadow cast by the Milky Way. I'm talking about having seen M33, the Triangulum Galaxy, naked eye in the sky. It's one of the largest, dimmest Messier objects, and under the right conditions, you can see it naked eye. You will absorb local colour and flavour and get the real Aussie outback experience, including snakes and spiders and all the other things that we're scared of. So that's my push. Give it some serious thought. If you do some homework and you start looking at the logistics, as I say, I discovered, for example, here, Devil's Marble, just up the road from there, there is the Devil's Marbles Hotel. Looks like a nice place. It's got rooms, cabins, sites for parking, camper vans and the likes. It's got camping sites, powered and unpowered. Guess what? It's booked out already. Okay, we are 3+ years away from this. And so the place is starting to fill up. And obviously, the further out here you get, whoops, that was me again. The further out here you get, the fewer and more sparse become your options. It is doable. You can get camper vans out of Alice Springs, which is down here, or Sydney, a couple of $100 a day, sort of 4-berth, self-contained camper vans, that sort of thing. So what I'm trying to stress here is the logistics are very plausible. It does take a bit of planning. You're not heading out in here, which is where people die, or out here where you've got Wolf Creek crater and so on, where people die. You're going to be in relative civilization, but it will take planning and some expenditure. So that's that. Finally, in passing, I was telling friends at home over the phone that I was doing this presentation tonight. Said one of my friends said, well, why don't you run a trip for your friends? I have to say I have started giving that some thought. So we may come back to that in a future presentation. So thank you. Any questions? Good. All righty.
Right on. Right on. You're right on the mark. You did. Thank you very much. That was great, actually. You certainly got me thinking about it. But yeah, you should give that some thought. Yeah. All right. We'll move right along to observation reports. We have a few. I know that May has been pretty dismal. Yeah. Actually, Oscar Echeverry, I think who left early, but our president, Oscar Echeverry, summed it up rather nicely for me a couple nights ago when it was supposed to be clear, but it wasn't. He sent me a text. He said, if it's not clouds, it's smoke. Anyway, we did squeeze in a few things here and there. And without further ado, Bob will show you his captures. There you go, sir.
Yeah, this is, by the way, I should say that a few days ago it was supposed to be clear and I set my scope outside and it freaking rained on me.
Sounds about right.
Yeah. And another thing about Mark Garneau, by the way, a long time ago, he came to our high school as an astronaut, and we had the presentation during the morning, and lunch came along, and our science department took him to lunch. And so me and 3 other guys got to spend an hour and a half with Mark Garneau. I do not know who covered my classes. No idea. Anyway, this is NGC 4236. It's one of Richard Taylor's monthly challenges. My first effort this galaxy was during the full moon, of course, and it was clear, but the images just sucked. They were all washed out and large gradients across the field. This image was taken another night without the moon. The galaxy is about 12 million light years distant and is part of the M81 group. Next slide, please, Chris. This trio is another of Richard Taylor's monthly challenges, and again, I tried in full moon and it was a disaster. The image was also taken without a moon again, and it turned out okay. The central galaxy is about 130 million light years distance and about the size of the our own Milky Way. It doesn't show up in my photo, but there is some disturbances in this galaxy suggesting a collision with another galaxy. I particularly liked the bottom face-on spiral galaxy in this image. Very pretty. Next slide, please. The Sunflower Galaxy is about 30 million light years distance and is about a magnitude 9 brightness. That means that you're going to need a medium-sized telescope to see it. Next slide, please. The Ring Nebula. This was the first object that I saw in a telescope. That was along with M51 and the Albireo double. It was it is a planetary nebula, which is a star that's blown off its outer layers. It is about 2,500 light years distance. You find it really near Vega, the star Vega, so it's easy to find, and most telescopes would resolve it. Next slide, please. This is just the same image, just cropped in, so you can see a little bit more detail. The nebula is expanding at about 30 meters per second. I'm sorry, 30 kilometers per second. Yeah, a little different. If you run these numbers backwards, you can figure out when the nebula was formed, and it was about 1,600 light years, 1,600 years ago. The red color is mostly from ionized hydrogen, and the blue is mostly ionized oxygen. You can see they kind of form a green layer there when they combine them. It's also being lit up by the central star of the nebula, which just barely shows in this image. Does it? Yes, it does. Thank you very much.
All right, Jim. There you go.
Ooh, that's a small one. Okay. So let's see. NGC 2282. I'm wondering, is that my image?
That is your image. Yep.
Really? Okay. M57. No, that's not my image. Oh, never mind. M57, the Ring Nebula in Lyra, over 2,500 light years away. And when I image the Ring Nebula, I often image it close up, but it's nice to see it in the wider context of how this planetary nebula stands out in the sky. The glowing remains of a sun-like star. For this image, I used the camera, a new camera that I purchased a couple of weeks ago, a Malincam DS83-800 color version. And I took that last week here in town. Next one. Yeah. Okay, these aren't the images that I recently gave you, but this is another one. Okay, so this is a solar animation. And I took this with a ZWO ASI 174 monochrome camera using fire capture. And I processed this with IMPPG. Unfortunately, I must have made a mistake because the image that you're seeing now is not the one that I submitted. But nevertheless, I hope you enjoy it. It's quite nice. Thank you very much.
Is this one of yours, Jim?
Yeah, but that one I submitted a while back.
Okay.
That's
Okay.
Yeah, those are previous.
We'll look into that soon.
Oh,
Got our-
that's another previous one. Yeah, okay.
You're okay? Sorry about that. We'll get that squared away for the next meeting. Malcolm. There you go.
Advance is the green or?
Yeah, the big one.
Yeah. This is another view of the Draco triplet, which we just saw. There were actually two nice nights in May, and actually with no moon, so took advantage of that. And on the first night, I photographed about 5 hours of RGB, the color information. Second night, the luminance, and then combined it together here to get this image. And let's see if I can. there we go. That's the names, the classifications of the three different galaxies. And a couple things struck me about this when I was looking at it. One was that as I look closely at the image, unfortunately, some of it's blocked up there, but I could see lots of other galaxies and a lot of small galaxies. And I started to do an analysis of this, and I found dozens and dozens, and maybe even to the hundreds. The other thing that struck me was the fact that these three galaxies all look quite a bit different. So I started thinking about, well, you know, how are they classified and why are they together? And as it turns out, they are a triplet, but unlike the Leo triplet, which is really a compact galaxy group, meaning that those galaxies are all very close together and gravitationally bound. These are really much more of a triplet because they visually appear in the same part of the sky, but the gravitational attraction between them is somewhat weaker. They're not so compact, and the distance is quite a bit further. They range from about 100 to 150 million light years away. So I took a look and did a detailed view of all the galaxies I could find within the image. And these are about the top 20 in terms of size. And there's all kinds of them in the field. And I found, let's see if we can, that there are about 4 others that are actually part of the same galaxy group. And as I did a little more research, found that the actual number of galaxies in this galaxy group, which is the NGC 5982 group, it's really unclear. It varies and depends on sort of which source you use, but it could be up to 16. And just to give you an idea of the size, the orange circled one that you see up on the right is that orange circled one down on the left in the larger picture. So yeah, these other 4. So now we've got the 3 original plus these 4. We've got about 7 different galaxies that are part of that group in amongst, you know, a field of many galaxies. And so this is a classification guide that's widely used. I think it was developed by Hubble for different galaxies. And it's not meant to show kind of evolution of a galaxy. So you don't read this as, oh, a galaxy evolves kind of from left to right. It's really just a picture showing, well, what does my galaxy look like? And therefore, how would I classify it? So you have ellipticals with varying degrees of roundness. And then ultimately, you know, these lenticular, right at kind of the beginning of this, where the galaxy spirals spread apart. And they're kind of in between an elliptical and a spiral. Then on the top, you have these kind of normal spirals, and on the bottom, you have barred spirals, where the spiral arms on the barred ones extend from what looks like sort of bar regions going through the core. So with that as the basis, I looked and said, okay, what are these galaxies we're looking at? And so there's the spiral NGC 5985. We see we have an elliptical galaxy. And this one, although it's not apparent because it's edge on, is a barred galaxy. And then the other 4 that made up, we see another range of different members with different degrees of, you know, how open the spiral arms are, and even a lenticular one here, which means that basically it does have a bulge in the middle, and then a round area, but no really distinct spirals to it. So it's kind of at that transition. And that's it. Thank you.
Good stuff. Thank you very much. Great. Oh, this is mine. So we did have a bit of a break, actually not that long ago, just a few nights ago. Last Sunday, in fact, there was a major auroral storm in progress, and the hemispheric power index at one point reached up over 250, which is hot for those of you that are not familiar with that index. I get excited about seeing auroras in our sky when it hits around 70 or 80. So it was hot, but unfortunately it was clouded. Fortunately, the storm that generated it lasted 3 days. And so on Sunday, we got a lesser storm. You can see the chart here. The two red bars on the left are the original storm on Sunday, topping out pretty heavy. But 24 hours later, about 24 hours later on Monday night, there was a resurgence, another wave that came through. And the blue bar that I've got in that is shows I've got a time lapse that I've shot of that. It occurred in that bar. So I was lucky to get that particular time when it was hot, because the occurrence on Monday wasn't nearly as strong as the one the day before. Still, it was pretty nice. You can see the extent of the auroral oval here. As you can see, the hemispheric power index is at this point, which this was assembled just shortly before I went out to do my photography, was just a shade under 100. It actually went up over 100 during the course of that interval. So it was a lucky break. What I found, though, was that even though these numbers looked good, when I got out there and set up my equipment, I really couldn't see anything other than a diffuse, maybe-ish green glow near the horizon. But I thought I'd wait it out and see if there were any surges, and it was fortunate that I did, because in this interval that I've got, and I'll show you the next shot here. There we go. In the interval I got, there were two phases that were about 3 or 4 minutes long where I could actually see these rays. And I've slowed down the video in those portions there because that's very fleeting. If I run the whole thing at full speed, you probably wouldn't see them. But yeah, so this is 72 minutes, and you can see that the bright portions were only minutes long. So at least caught a piece of it there. There's a little bit of a resurgence there. And that's when I packed it in around 1 o'clock or so, and I don't think it did much in our neck of the woods prior to that. So even though we hadn't had many clear nights, it was fortunate to get this particular one. Okay, I think Richard. There we go. Richard's got something to share with you, and also our challenges for the following month.
Yes. Okay, just before I begin with my observations, though, I thought it would be worth mentioning, sadly, another person who passed away on June the 1st was Fred Espenak, who everybody knows as Mr. Eclipse. He's been the NASA's go-to guy for eclipse predictions for many, many years. He's actually seen, I think it was 55 eclipses in his life. So he passed away on June the 1st. I'm very sad to hear that. The other thing I wanted to mention briefly, in conjunction with the presentation about in the news earlier on about light pollution, our own Rick Scholes did a wonderful presentation at a meeting of the town council in Mississippi Mills, or Almont, trying to stress the need for better regulation of the LED lights outdoors so that we can keep our FLO as dark as possible. And it was very well received. There were quite a number of us in the audience who were obviously there and interested in that matter. So thank you to Rick for doing that presentation. Okay, so these are my observations for the month. I mentioned that Draco was a very interesting constellation, so I did try and get a picture of it here, and it's not a very bright constellation. The most prominent thing I find is, oops, sorry, let's go back. If you're looking up into the sky, obviously people know the Big Dipper here. And then following the pointer stars to Polaris. And then if it's dark enough, and this was taken from FLO, you can see the curve of the Little Dipper, or Ursa Minor. Where's Draco? It's sort of in between. So there's a curve of stars that you can see going around the bowl of the Little Dipper. and then it bends sharply and comes to this little trapezium, if you like, which is the head of the dragon. I always find it looks more like a diamond shape, and that's directly above Hercules, which is down here. So that's how you can find the constellation. In the next slide, I've connected the dots to see it more usually. But of course, when you're looking at the stars at night, you don't see those lines. So you have to imagine it all, and you have to keep an eye out for particular shapes that help you identify things. Now, the next picture is going to be zooming in on this particular area up here. And that's where I noticed an object that's quite interesting in binoculars. It's this kind of trail of stars in here. And with binoculars, you can definitely see a kind of arc shape, a cascade of stars. And there is the little galaxy that Bob Olson had a much better picture of. This doesn't show up very well in binoculars. It's a very, very faint galaxy because it is quite large, so the light is spread out by quite a bit. But when you zoom in on it, it's really quite a fascinating galaxy. It does require a dark night, but then there's all kinds of interesting star clusters and star forming regions in this galaxy. So I definitely recommend it as a astrophotography target. And then the Draco triplet that you've seen several times, and thank you, Malcolm, for that very detailed explanation of the different classifications of the galaxies. Like Malcolm, I noticed that there are quite a few other little galaxies. I can see them on the screen in front of me, but they're kind of difficult to see. But there's this one here that I found quite prominent, and there's another one up in this region here as well. That's a closer view of the three main ones, and I've tried to sharpen the picture so that you can see the dust lanes both in this face-on spiral, and also there's a kind of streak of dark dust lane in that edge-on galaxy as well. And then the solar system challenge for this month was the Altai Scarp, which is a secondary rim to Mare Nectaris here. So this is the Altai Scarp in this region. So you can see it's kind of concentric with the Mare here, but quite a bit farther out. And it does show up very nicely at just before the first quarter phase of the moon. So those were the observing challenges for this last month. And I'm very happy to see so many pictures tonight of the challenge objects. That makes me feel I'm doing something useful by pointing out these objects. On the Discord server, we had quite a few other pictures, and Jim Thompson actually pointed the Altai Scarp out to me on Astronomy Day through his eyepiece. So a lot of people were noticing that one. On the Discord server, we had Tony Jarrett and Xavier managing to capture many of these things. And Tony actually managed to see and draw NGC 4236 using the 18-inch telescope. So that was quite an interesting thing. If you're on the Discord server, go and take a look at that. So for the coming month, we have the constellation that's just a bit south, as I mentioned. You have the head of the dragon here, but it forms a kind of diamond shape with one of the stars in Hercules. The most easy thing to see in the constellation of Hercules is what's called the trapezium, this set of 4 stars here. And then there's the arms and legs, which kind of stretch out in different directions from the central portion. Now for the next level challenge, if you're looking at Hercules in binoculars, well, the first thing you're going to notice is there's a fuzzy patch right there, the great globular cluster in Hercules. And I thought, well, you know, while we're looking at globular clusters, and that's the thing at this season, there's a lot of different globular clusters surrounding the Milky Way. And at this season of the year, the Milky Way is going to be rising fairly late in the evening. But before it does, take a look at some globular clusters. Not only is the M13 a nice big prominent site here, but also making a triangle with the two widest separated stars in the trapezium is M93, which is another, sorry, M92, which is another very nice looking globular cluster. And that's not all. There is yet another globular cluster up here in this region, quite a bit smaller, definitely a telescope object, but it's still pretty bright. So it doesn't need a very powerful telescope or a long exposure to capture them. So those are the challenges for this month. M13 with binoculars, M92, small telescope, and then NGC 6229, another smaller and fainter globular cluster. For the solar system challenges, I think I'd like to recommend that you keep an eye on Mars. It's not a great telescope object at this time. It's moving away from us. It's getting pretty small. You're not going to be able to see too many features. But there's some interesting close encounters this month. June 16th, it forms a lovely small pair, very close together with Regulus, which is a star of a similar brightness to Mars. So it's going to be very interesting to take a nice snapshot of those two together. And then at the end of the month, it has an encounter with the moon, very close and not here, but in some places it will actually disappear behind the moon. So see if you can have an eye on that. It will be in the west just after sunset. And of course, sunset is going to be pretty late at this time of year. So you have to have a good view towards the west in order to see these incidents. So good luck and happy observing.
Thank you, Richard. All right. Few last announcements before we call it a night. Public star parties coming up for this year. June 27th/28th is our next scheduled party. As you can see, there will be a waxing crescent moon, but only a very small percentage, so pretty much as dark as we get. So we'll cross our fingers. Hopefully we won't get smoked out by that. We'll see. And if you're not familiar where we hold these star parties, it is at the parking lot for the Diefenbunker site in Carp, in the main parking lot there, as is indicated, right there. That's the parking lot. There's the Diefenbunker site itself and the Carp Library. All right. Also, we're looking for volunteers for the star parties. So if you're game to come out, then you can bring your telescope, or you can just help us with general traffic control, because sometimes these are really well attended, especially when we got a clear night. And also just helping out with support, directing people where there are, things to see and what to avoid, that type of thing. So again, if you can help out, we appreciate we would appreciate your volunteering. Timing goes from 8 p.m., where it's still going to be fairly light, to about 10:45 p.m. And you can see the contacts there that we have at the bottom for letting them know that you're interested in helping us out. So we would appreciate your stepping up on that. Just notice Fred Lossing Observatory also available now, 3 telescopes up and running. Just trained a new person on the 16-inch, so John Madden joins our club. And so these are accessible again to members of the club that have been trained. You can talk to myself or Rick Scholes about receiving training on these instruments if you're interested. FLO star parties. as opposed to the ones at CARP. These are for members only. Our next one is June 28th, where again, we're dealing with just a waxing moon. So again, fingers crossed, hopefully we'll have a nice weekend for that, and maybe we can get a chance to see Richard's close encounter between the moon and Mars. Estelle's pick of the month is planetary astronomy, and Estelle is available to show you the library if you're so interested. Just various club information there. Again, Rick is our FLO director. Estelle is our book librarian, and Peter Shute is in charge of our telescope equipment loan library. And if you have any questions at all about your membership, please contact Art Fraser. I have one further announcement that's not on here. I'm going to be kind of not available for most of this coming month. We've got a few trips and hikes and camps on our family schedule there. So next meeting is on July 11th, and Jonathan King is going to be your host there. So in the interim, if you have any questions at all that you would normally direct to me as meeting chair, John doesn't have access to that account, to that email account. So please send me the message at meeting chair. I will have intermittent internet access, but John will be your man for contact. So it's just CC him on any questions you have or suggestions if you want, if you want to do a presentation, or as we get closer to the date of the meeting, if you've got some observations you want to share, let Chris and John and myself know. Okay. All right. I should go back and see what we had there. Oh, sorry. I think I'm flashing the wrong one. I hope it didn't burn out anybody's eyes there. So we have 49 folks here today. Hope you enjoyed the program and found a few goodies on the swap table. And we had 35 on Zoom for a total of 94 today. And I thank all the presenters for their hard work in helping us organize and spending their time and efforts on the presentations that you've seen. And again, thanks to the RASC National Office for their use of their Zoom facilities. So again, any comments you have at all, good, bad, in between, send them to meetingchair@ottawa.rasc.ca. Not the dash one, that's the bad site. All right, I think our final slide, there we go. There we go. For those that are interested, we have our usual post-meeting meeting at Liam McGuire's at 1705 Saint Laurent. So you're welcome to come and join us there. And our next meeting will be July 11th, not the 4th. It'll be the second Friday in July due to the holidays in the week before. So hopefully I'll be back at that point in time too. But as I say, Jonathan will do a good job manning the show, and we'll hope to see you there. And I wish everybody clear skies. Take care. Am I? Oh, I am too. Complete with sun shield. Thanks, everyone. How's it going? Oh, it's going good in there. Cross it right now. So he says, yeah. Yeah.